So now we're engineers, and we're trying to figure out how to design this roadway. What angle, theta, should we make the banking of the road? And we want to make it so that when a car goes by at the speed limit of 35 miles per hour, that it doesn't need to use any friction to keep it from sliding up or down the road. So we can start writing a free body diagram here. We know the normal force always goes perpendicular from the ground. And we know in this case that if this car is driving right at us, it's curving along the road here, so it's going to end up going, following a circular path. So because it's going in a circle, we know that this normal force, one component of it is going to be providing the centripetal force that's going to radially accelerate this car toward the middle of that circle. And the other component of the normal force is going to be exactly opposing the gravitational force pulling the car down. So this vector here, the vertical component of the normal force, must be equal and opposite to the gravitational force. So we can call this the vector of magnitude mg going up. And we know that because this angle here is theta, that we can say that this vertical component of the normal force is Fn cosine theta. And likewise, we can say that this component, this horizontal component of the normal force is, down here, is Fn sine theta. And the first step here would be to put this expression for the radial force in terms of mg and theta, some variables that we have values for. So let's take this equation, I'm going to rewrite it over here, and let's use that to solve for the normal force Fn. I'm going to divide both sides by cosine theta. Now we have a definition for Fn. So we can plug in this definition for the variable Fn, and we get our radial force is equal to mg sine theta over cosine theta. And we know that the equation for the radial force is mv squared over r, so let's just put that in there instead of fr. So now we have an equation with the variable we want to solve, and it's in terms of variables whose values we know or that we can cancel out. There's an m on both sides here, so let's cancel out the m. So that's going to make the m's disappear. But in this step, let's also do another thing. We'd prefer to have just one unknown variable instead of two of them. So let's rewrite sine over cosine as tangent, because that's what tangent is. It's sine divided by cosine. I guess you just have to know that. So we get this equation now. We've simplified it a little, and now we can really get down to the business of just solving for theta. So let's divide both sides by g and put in the numbers we know. Here is how not to put in the numbers. Notice that we did not make the units consistent. We have distance of mile and meter, we have time of hours and seconds. If we go ahead and do this multiplication and division, it's going to be a cluster storm of different units. We don't want that. It's not going to give us anything that's correct. So what we have to do is convert units. We have to convert the 35 miles per hour into meters per second. and I googled a conversion factor for that. There are 2.2 miles per hour per 1 meter per second. So what that means is 2.2 miles per hour is equivalent to 1 meter per second. When we multiply by this conversion factor, we're canceling miles per hour, and we get 15.9 meters per second. So what this is going to be the number we use for the velocity. So I'm going to go ahead and put that in, and I'm not going to forget to square it. And that's the number we get. For tangent of theta, to find theta, we take the inverse tangent of 0.955. And when I take the inverse tangent, it tells me that theta is 43.7. And that is a whopping heck of a lot of curve. It's a lot of banking for the road to have. So when doing the reasonability check, we have to get a little suspicious. But I think I kind of just picked random numbers for this question, for this example. And I think that a radius of curvature of 27 meters is probably a pretty small radius of curvature. That would be a very curvy road. So I'm thinking that this road needs a lot of banking because it's a really tight turn. But if you think I did something wrong, or if you have any comments, or you think anything needs corrected here, please do comment or send me an email.